In this video, we're going to talk about pure resistors and pure capacitors in AC circuits. A pure resistor is one whose capacitive and inductive effects are negligible. If we have something like this is the AC source or AC supply. This is the resistor. From this point to this point is the voltage, and current is in this direction. So this is a resistor in AC circuit. Okay, now if the current in this circuit I is equal to I naught sine 2 pi f t, then the potential difference will be V. Remember, V is equal to IR. It will be I naught R sine 2 pi ft. So we can replace and say it is equal to V naught sine 2 pi ft. And because of that, V naught, this is because V naught is equal to I naught R, that's the peak. For pure capacitor, a pure capacitor has no resistance or self-induction. Okay, now suppose that the alternating potential difference applied to the capacitor is given by V equal to V naught sine 2 pi ft. The instantaneous charge on the capacitor will be, because Q is equal to CV, it will be now C. Instead of V, we will now replace it with V naught sine 2 pi ft. From the equation that I is equal to dq over dt, we can arrive and say that I is equal to d over dt. Instead of writing Q, we replace Q with this by saying C V naught sine into 2, let's make here a big bracket, 2 pi ft. Now, having gotten that, we can still say is equal to CV naught into 2 pi f cos 2 pi ft. So from that we can arrive that I naught is equal to sine into 2 pi ft plus pi over 2. And because of that, we have to try. We can arrive that V naught over I naught is equal to 1 over 2 pi fc. Now this is the peak current. Alright. Now if we have a sketch and we say this is I and V, if we have the current goes this way, to go this way, this point is the I naught, peak I naught. The V naught voltage peak will still be from 0, goes this way, goes this way, goes this way, and so on. It continues. Now, the variation of the current I and the potential difference with time. Okay, this is time. Now, here is V. This one is I. You can know that this is a phase diagram for both of them. And the both of them are in phase because they begin from 0. They begin from 0. they are in phase. So on the other hand, if we connect a capacitor to AC, the first one was connected to resistor. Here now we connect it to AC. Let's sketch beside. If we connect it to AC, let's say here is I and V plotted against time. Against time. Here is time. So this time. Here is time. So what we will notice here is that for current will begin from here and will go this way and so on. But for voltage will begin from here and so on and so forth. So this is current while this is voltage. Okay, when we compare this now, you will notice that this phase diagram shows that V, potential difference, and I are not in phase. The phase difference is pi over 2, or you say 180. So if you put it in radian, that's pi over 2, or you say 180 over 2, which is 90. So radians, or you say since pi is 90, so 90 pi is 180. 180 over 2 becomes 90. So in this case, you notice that the current leads by 90. It leads voltage by 90, or by pi over 2. So since I is equal to I naught sine 2 pi ft plus pi over 2. So you will notice that the current is at its peak when t is 0. You see that. On the other hand, potential difference V is at its peak only after a time of t over 4. So that's if you have cycle over 4, divide it into 4. Okay, which is equivalent to phase, which is what we say pi over 2. Okay, so because of that, we say that V naught over I naught is equal to 1 over 2 pi f c. So we can replace V naught because we said that V naught is equal to root 2 VRMS, and I naught is equal to root 2 IRMS. We can replace V naught over I naught, that's peak, equal to V2 VRMS over root 2 IRMS. So which is equal to VRMS, because this cancels out this IRMS. So this ratio is known as reactance, denoted as this. So reactance of a capacitor. So the reactance of a capacitor, it is given as V naught over I naught. That's also equal to VRMS over IRMS, also 1 over 2 pi fc. So any of the formulas go. Let's look at an example. This question says, if a 50 microfarad capacitor is connected across an alternating current, an alternating EMF described by V equal to this in volts, calculate the capacitive reactance for this circuit, determine the maximum current through the capacitor. Now, we need to know that the capacitive reactance is given as 1 over 2 pi fc. Okay, now f is frequency. They did not give it to us. Now, capacitance, C is capacitance, which is, they gave it to us to be 50 microfarad, which is 50 times 10 raised to power minus 6 farad. Okay, now from the question, they gave to us that V is equal to 30 sine 2000 pi, okay, 200, okay, the question is supposed, 200 pi, since it is 200 pi t. Okay, now let's compare. If we compare V equal to V naught sine 2 pi ft, if we compare both of them, here now they look alike, so we can say 200 pi t is equal to 2 pi ft. Here pi is on both sides, so we cancel. T is on both sides, we cancel. What it means is that 200 is equal to 2f. 200 is equal to 2f. Therefore, f is equal to 200 over 2, which is 100 hertz. Having gotten f, we can now use our formula, this, which is equal to 1 over constant 2 times pi is 3.14 times another 10 there is f. F is 100 times c. Our c is 50 times 10 raised to power minus 6. So this is equal to 1 over 0.0314, and if you divide 31.847 ohms. The second question says we should determine the maximum current in the circuit. Okay, now they gave to us that peak voltage V0 is 30. Peak current is what they want us to find, and we have already gotten that capacitive reactance is 1 over 2 pi fc. We already got it to be 31.847. Okay, now remember the formula that says that capacitive reactance is equal to V naught over I naught, their relationship. So what it means is that 31.847 is equal to V naught is already 30 over I naught peak. So peak, subject of the formula, becomes 30 over 31.847, which is 0.94 ampere. Please remember to subscribe to my channel if you haven't. Thank you.